Okay, welcome back. We're going to finish up section 10.3, which was about the dot product today. And then we're going to move on to section 10.4. Okay, so from last time, we were talking about the geometric meaning for this dot product. And we figured out by the law of cosines that if we have two vectors and we're dotting them together, this is equal to the magnitude of A times the magnitude of B times cosine of theta, where theta was the angle between the two vectors on a shared plane. Okay, and we could just easily algebraically manipulate that so that we would have cosine theta is equal to our dot product of A and B over the product of their magnitudes, right? So this kind of gives us a way to find that angle theta between the two vectors, right? So that's kind of one geometric understanding of the dot product. So now here, let's do an example. So we're going to find the angle. Oh, where did my paper go? Oh, here it is. Between this A vector, which will be 1, 2, 2, and a second vector we'll call B, which is 3, -1, 2. Okay, so I can use the above formula that I've got here for cosine theta, but notice that we're going to need both the magnitudes of the vectors as well as the dot product. So let's go ahead and find those. So let's start with the magnitude of A. Write this as the square root of 1 squared plus 2 squared plus 2 squared. This is equal to, inside here we just have 9, so we get just equal to 3. And then the magnitude of the B vector is 3 squared plus -1 squared plus 2 squared. And this gives us the square root of 14. Okay, and we need one last thing. We need the dot product of A and B. Well, we can use the alternate definition for this, for the calculating the dot product. So we do the multiplication of them component-wise right here and add up those multiplications. We get the first element times the second element, so 1 times 3, plus 2 times -1, plus 2 times 2. And here we just get 5. Okay, so now this is everything that we're going to need to calculate this right-hand side. So then we have that cosine theta is equal to our dot product over the magnitude of our two vectors, which we found 5 and 3 and the square root of 14. Okay, so this means that theta is arc, not tangent, cosine, arc cosine of 5 over 3 root 14. And if we just happen to just plug that into a calculator to get an idea of what kind of value we should be looking at here, this is 1.109 radians. But as a final answer, symbolically, we can just leave it as this guy here. And this is the angle between our two vectors, A and B. Okay, so let's kind of introduce some definitions here. We say that two vectors are called perpendicular or the more commonly used that we're going to use moving forward, or orthogonal. If the angle between them is pi over 2, or a right angle. Or what we can do is we can also notice that A dotted with B is equal to the magnitude of our vector A, the magnitude of our vector B, and we have that the angle between them is pi over 2. But this cosine here just gives us a 0, so it doesn't matter what the magnitude of A and B here. So we just get the scalar 0. So the dot product is a way to find out immediately if two vectors are orthogonal to one another. As if their dot product is equal to 0, we know that they're going to be orthogonal. Okay, so let's do an example with that. Let's show that the vector I plus 3j plus k and the vector negative 2i plus j minus k are orthogonal. Okay, so this all just boils down to is their dot product equal to 0. If I can show that, then I know that they're orthogonal. So let's go ahead. We have I hat plus 3j hat plus k hat. And we're dotting this with our vector negative 2i hat plus j hat minus our k hat. So we conduct our dot product here. So we get 1 times a negative 2 plus a 3 times 1 plus 1 times negative 1. Well, right here we get a negative 2, we get a 3, and then we get a negative 1. So it looks like our dot product is 0. So this means that they're orthogonal, and that's all we really had to show. We just said that their dot product was equal to 0. Okay, so another neat little thing is if we have that A and B are in the same direction, A dotted with B is equal to the magnitude of A and the magnitude of B. And that cosine disappears because it will just be either cosine, it would just, since they're in the same direction, thetas should be 0. So we'll just get cosine of 0, and then it just becomes 1. Not as useful because you can simply see if it's a scalar multiple, but it is a nice little trick that if they're pointed in the same direction, their dot products will simply be the magnitude of the product of their magnitudes. Okay. Ooh, now, yeah, that's right. Now we're doing projections. So let's do a new page here. Let's talk about projections. My experience, this is the first kind of small hurdle for students, so we'll take our time on this. So now that we've introduced this dot product, we can kind of discuss what it means to project a vector onto another one. It's probably best to kind of do this in picture form. And what do I really mean by that? So imagine that I have one vector here, and I have a second vector here. And we can actually go ahead and name these. So here I'll have my A vector, and I'll have my B vector here. And the idea is I'm going to project B onto A. And let's actually do this in a different color now. So when I project B onto A, I have to follow A. So I have to be on A, but I go as far as the line so maybe I should redraw that guy right there. As far as that line goes to here. And you can think of it as B is casting a shadow onto this A vector. So let's go ahead and say this is like the shadow of B on A. Right, so the sun's coming down and the shadow is kind of projected onto this A vector here. Okay. So this shadow is called the vector projection of B onto A. So here we have the vector projection of B onto A. And is denoted by like proj standing for projection, and it acts on B, and its supplement is a subscript underneath A. So this is read as the vector projection of B onto A. So input is a B, and it's kind of like this parameter is A. And we kind of denote that as this like little subscript here. Okay. So let's also say that the projection doesn't even need to end on A. But along the direction of A. And what do I mean by that? Well, let's do kind of the same kind of scenario that we did up above, but this time, let's have some A vector, and I'll have a B vector that points now over here. Right, so this is our A vector. Here we have our B vector. Let's do a color change here. Our shadow still goes directly downward here onto the direction of A, but it doesn't get cast over here. It doesn't end on A. It just has to be in the same direction as A. So the shadow that it casts is over here now. So this is the, that's a straight line. This right here is our projection of B onto A. That's the little shadow that it casts. Okay. So let's kind of work with what happens with this shadow. Let's try, figure out a few kind of characteristics of it. So the magnitude of this projection. So the magnitude of this projection is known as the scalar projection. So it is the component of B along A. So basically it's basically just denoting what is the magnitude of this shadow here. That thing is called the scalar projection because the thing that comes out of it is a scalar, right? I get the magnitude here, but I get the direction as well when I look at the vector projection. Okay, so let's use the dot product to help us figure out what this magnitude is, because we can note that A dotted with B is the magnitude of A times the magnitude of B times cosine theta. Well, I'm going to write this in kind of such a way. I'm going to put parentheses around these two terms here. These two things, the magnitude of B cosine theta, this is in fact the length of the shadow right here. This is the length of shadow. Right? If you just look at, if this is our angle theta here, so let's kind of just draw that in. So if we have our little angle here, this is theta. Oh, sorry, should actually be, let's draw it on this upper one up here. So this is our theta, right? This length right here is simply cosine times the length of B. Right? So that's the length of our shadow. But we can also use this in the context of our dot product to write that the magnitude of B cosine theta is equal to the component, and this is how we kind of denote this scalar projection, of B onto A is equal to A dotted with B over the magnitude of A. So all we've done is just solved for the length of the shadow using our dot product. And now what we've done is just given it a like a way to write it. This is the component of B along A. This is the scalar projection. What is the magnitude of that shadow? Okay. So now that we have the magnitude, in order for us to get the vector projection, we need to travel in the direction of the shadow now. So let's kind of scroll up and kind of just think about this for a second. We now have what this length is, right? We have our scalar projection. We have a way of writing that down. But what we need now is the direction that the shadow is headed in. Okay, that's fine, because we know that it is along the vector A. But we don't want to really mess with the magnitude, right? We don't want to mess with this length. So what we could do is introduce a unit vector that points in the direction of A, right? So we need a unit vector in the direction of A. Okay. Well, if I have any vector and I scale it by how long the vector is. So imagine that I have a vector of length 5 and I divide it by 5. That would mean that its new length would be 1. So a clever little way to get a unit vector pointed in the direction that you want is if you write it like this. So this is the original vector A, and now we divided it or scaled it by 1 over its length. This makes this a unit vector. So this is a unit vector. Along A. And we'll use this trick pretty often in this class. So if you need to make a unit vector pointed in the direction of another vector, you can just simply scale it by its magnitude, or 1 over its magnitude. Okay, so now if this is the direction that it's going, and we have the magnitude, the scalar projection right here, we can just write down that the projection of B along A is the component of B along A times A over the magnitude of A. So right here we have the magnitude. And right here we have the direction. And we can sub in what we wrote down for the component of B along A. This is the dot product between A and B all over the magnitude of A. And we're multiplying this by the vector A over the magnitude of A. This right here is equal to A dotted with B over the magnitude of A squared times A. So notice the thing out in front here, this is still a scalar, right? Because we're doing a dot product. And we talked about how the result of a dot product is still a scalar. The magnitude's a scalar. So this is just a scaling factor out in front of a vector A, the vector that we're along. So this is now our definition for our projection. Right there. Great. So now let's go ahead and use this information in an example. So let's scroll up just a little bit more, give ourselves some room. So we're going to find the scalar and vector projection of the vector B, 1, 1, 2, onto the vector A, which is -2, 3, and 1. Okay. So let's start with the scalar projection. And notice that, I'll kind of scroll up here for a second. So notice that both of the component or the scalar projection here involves the dot product and the magnitude of A. Same thing here, right? So I'm going to go ahead and pre-calculate those for both my scalar and my vector projection. So, well, I know that the magnitude of A is equal to the square root of -2 squared plus 3 squared plus 1 squared. This gives me the square root of 14. And I also can calculate the dot product of these two. So I'll look at A dotted with B. So I get -2 times 1 plus 3 times 1 plus 1 times 2 is equal to 3. So then I have that my scalar projection, or my component of B onto A, was this dot product divided by the magnitude of A, or 3 over root 14. So that was the length of the shadow of B onto A. To get the full vector projection, so our projection of the vector B onto the vector A. We can write this as the component of B onto A over A magnitude. Or we could also calculate it with our dot product and the magnitude of A squared times the vector A. And either way, we get 3 over 14 times the vector that was A, which is -2, 3, and 1. So we can go ahead and bring out that scaling factor of 3/14 into our vector. So we get -3 over 7. We get 9/14. And then we get 3/14. And that is the vector that denotes the shadow. Will you ever have a smaller magnitude than B, or does that not work? You should be getting that the magnitude of the shadow should be less than the magnitude of the vector that it is coming from. But it could be larger than A, right? Notice that the length of A doesn't really, if you look at this right here, the length of A doesn't really form into the length of the shadow itself. These magnitudes here are just to denote this unit vector into the direction. So we could have that the shadow that's cast from B is longer than A, for sure. Yeah. Okay. So one last thing before we kind of finish up this section. We're going to introduce work. Okay, so before I talk about work, the work that we've talked about in the past in maybe Calc 1 and 2, and the work that it will present here is when the force and the distance are constant things, right? I'm going in a straight line with a constant force. I can do it this way. Otherwise, I would have to get a little bit more intricate, and we will discuss how to do this later on in the course. So you might have seen in previous physics classes that the work, which we'll call W, is equal to the constant force times the distance that you travel, right? So now, but this is only true when we're directed along the direction of motion. So we have to be a little bit more cautious, right? Because if the force is kind of acting in the direction of motion, that's fine. We can calculate this. But there's actually a vector form. So force is a vector, right? It has a magnitude, which you can measure, but it also has a direction, right? The Earth is pulling you down, right? So we have to talk about this in a vector form. Well, work is not a vector, but what it is the magnitude of F times cosine of the angle between the direction of that you're traveling in, and then the magnitude of this distance vector, right? So notice that this looks eerily similar to something that we've kind of talked about in this section. This right here, this is the dot product between these two vectors. So we can actually write this as the vector denoting the force dotted with the vector of the direction that you're traveling in. And in that sense, it is just f times air quotes d, right? But we have to be a little cautious here, right? Because these are now these vector quantities. But we do get a scalar out of this, which is the work done. Okay. We're at 120. Does this permit negative work if pi over 2 is greater than theta? No, you can't have, well, you can't have negative work. So if you have that theta is greater than pi over 2, then one, the force that you're looking at being applied here is not the responsible force for the motion itself, right? Otherwise, the object would be moving in the other direction. But let's say, you know, I'm on a bus and I push a box backwards. It all depends on your where you put your origin and your coordinate frame. Typically, you would like force to be this positive quantity. But if you know I'm pushing a box back to the back of this bus, I'm putting in some work. I'm putting work onto this box here, but the box still really is moving forward. So it all depends on what your reference frame is. It's typically physicists don't like to put down negative work, and I'm sure that's conveyed as well as into engineering. So you might want to pick a suitable coordinate system for that. Yeah. Okay. So let's move on to the next section. So we're at 120. And we're going till 2:20. So why don't we take our 5-minute break here, actually, and then we can dive into 10.4. So go ahead, get some water, go use the restroom. Let's reconvene in about 5 minutes. I was muted. Thank you. Okay. So before we talk about doing this cross product, we need to kind of do this determinant. Before we talk about what this, like how to do this determinant, we have to kind of talk about what it means to do this determinant of order 2. So basically what we're doing is we're writing these vertical lines to denote this determinant, and it acts on this array of numbers, A, B, C, and D. And the reason why it's called order 2 is because there's a 2 by 2 matrix in here. And we're not really going to talk about too much about matrices in this class because that's going to be more of a topic for diffie-q and linear algebra. But we need the determinant in order to do this cross product. So we start with this, and the way that this is calculated is we look at the diagonals. So I have AB here, or sorry, AD, and I have BC here. So this determinant is written A times D minus B times C. And that's all we need to go to do determinants of higher order. We just need the 2 by 2 determinant. So we have to kind of just memorize this. This is AD minus BC, and you can kind of think of that as just these diagonals here of this 2 by 2. Okay, so the determinant of order 3 breaks into 3 determinants of order 2. So an order 3 determinant looks like A1, A2, A3, B1, B2, B3, C1, C2, and C3. So I have this 3 by 3. So hang on, we have a question about what is a determinant. This is a determinant. It is how we kind of write out this operation that acts on a 2 by 2 array of numbers. And we're gonna have to learn what this is in order to do this cross product. So we're gonna kind of convey what that means for vectors in just a moment here. But if I have these scalar values in here, just use this as kind of a guideline when I'm doing the determinant of order 2, or this 2 by 2. It is just AD minus BC. So now if I have an array of 3 by 3, what I'm going to do is I'm going to move across the first row here. So I'm going to draw a little arrow here. And anytime I am at one element, I'll write that down. So this is equal to, ooh, those are arrows now. Right, this is equal to A1 times, and what's going to happen here is I'm going to cross off this column and the row that it's a part of. Right, so I have A1 here, and I crossed off its row, and I crossed off its column. And what's left is a 2 by 2. Well, I'm going to multiply A1 by the determinant of this 2 by 2. So this is A1 times the determinant of B2, B3, C2, C3. Next on the list is I move over in this row. So let's kind of get rid of this column here. And I'm at A2. You'll kind of discuss why this happens, but for now, just kind of believe me that we get a minus sign here, and then we get A2. And then I have to cross off this column that we're at now. And notice that I still have 4 numbers left, right? And this is another determinant, B1, B3, C1, and C3. And then we have one more to go, this A3 element. So let's get rid of that. We'll draw a new column here. We've crossed off this row and the column that it's a part of. We switch signs one more time, so it always alternates between signs that is positive, negative, positive. So we get plus A3, and then what's left is this determinant here. So this is B1, B2, C1, C2. So that's what I mean when we're splitting up this determinant of order 3 into 3 different determinants of order 2. So we're going to talk about what it means for vectors, not just for matrices. So we know how to do these 2 by 2s. We've got this determinant of order 2 right here. We know it's just this AD minus BC. So we can do the determinant on each one of these determinants of order 2 here. So we can actually write it out in full as A1 times B2 C3 minus B3 C2 minus A2 times B1 C3 minus B3 C1 plus A3 B1 times C2 minus B2 times C1, and end that. So if it's a little confusing about how to do these determinants, you can just take this at face value that this operation on this array of 3 by 3 numbers just gives you this result down here, right? It might be good to kind of review this. You will definitely be doing a lot of determinants for diffie-q, but we kind of need this for the operation for the cross product. So let's just do a quick example of doing a order 3 determinant on some array of numbers. So let's look at the determinant of 6, 1, 1, 4, negative 2, 5, 2, 8, and 7. Okay, so we need to break up this determinant of order 3 into 3 different determinants of order 2. So remember what we're doing. We're moving across this top row. So I'll already kind of cancel this top row out. And then we go one by one through these columns. So the first column in this row has a 6. And then when it comes down, it crosses off everything but these 4 numbers here. So this is the determinant of negative 2, 5, 8, and 7. Next, we switch signs, so we go to the negative. So we go -1 times the determinant of everything that's not crossed off when I cross this column off, which is this 4, 5, 2, and 7. Finally, I switch signs again, so I have a plus. My third element in this top row is a 1, so I'll write a 1 here. And then I have the determinant of everything that's left over when I cross off that column, which is 4, -2, 2, and 8. So now we can write this. We can do the determinants of order 2 here. So this is 6 times -2 times 7 minus 5 times 8 minus this 1 times the determinant of this order 2, which is 4 times 7 minus 2 times 5. And then finally, we have this plus 1 times this determinant, which is 4 and 8 minus -2 times 2. What we have here is 6 times -54 minus 1 times 18 plus 1 times 36. This ends up being -306. So that's what the determinant of this array of numbers is. This 611, 4, -25, 2, 8, 7. We take the determinant of this little block here, and we end up with -306. Okay. So I know this is kind of out of left field that we had to introduce this determinant here, and we're definitely going to try to get some practice with homework assignments and WebAssign, but we need this in order to kind of figure out what this cross product kind of represents here. Okay. So now let's define what it means to do a cross product. So now we define the cross product for A, and we write a cross here. Oh, actually, before we do that, let's define what A is element-wise. A1, A2, A3, and the B vector, B1, B2, B3. So notice that these are in R3, they're three-dimensional. We write A cross B. So this is how we denote the cross product here. So with this X multiplication, pretty much, this cross is equal to the determinant where the first row is I hat, J hat, and K hat. The second row is the A elements, A1, A2, and A3. The bottom row is B1, B2, and B3. So this is how we define the cross product. And because this is a determinant of order 3, we can do the same thing like we were doing above, where we'll expand across the first row here, right? So using the same kind of system as what we did up above, we can write this as equal to I hat times the determinant of A2, A3, B2, B3, minus J hat times the determinant of A1, A3, B1, B3, plus K hat times the determinant of A1, A2, B1, and B2. Don't think about this as a matrix that has scalar and vector entries. It's kind of how we systematically define this cross product. And it seems like we're putting this array together where we have vectors and scalars. But at the end of the day, this is what the cross product does. And a neat way of representing that is this determinant that we've got here if we had put in I, J, and K hat in the top row. So we can continue doing these determinants here. So the X entry is everything that's on this I hat, which is just A2 times B3 minus A3 times B2. The next entry is everything that's on this J hat, and keep in mind that we also have this negative here. So we have A3B1 minus A1B3. I just kind of swapped the order because we have this negative. And then we have A1 B2 minus A2 B1. And this is everything on the K hat. So when we end up doing this cross product of A and B, you can see that it's a little bit messier than the dot product, right? We get some jumbled entries here for sure. But another thing to note is that the result is a vector. The dot product resulted in a scalar here, but here we have a vector. So they both took in vectors, but their output is completely different, right? The dot product resulted in a scalar. The cross product results in a vector. Okay. So what does this even mean? Why would we go to such lengths to write what seems a lot more complicated than like the dot product, right? Why would we implement this cross product? Well, hopefully I'll convince you as we start to go here. The first thing is this theorem where we have the vector that is the result of crossing these two vectors together is orthogonal to both A and B. That's really cool, right? So if I give you an A and a B, simply by taking the cross product between the two, you've given me a new vector that is not only orthogonal to one of them, but it's orthogonal to both A and B. And that's really helpful. Yeah, we're going to see how we're going to implement this in a lot of different ways, getting some third vector that's orthogonal to both A and B. So another way of kind of describing this relationship is via the dot product. So the resulting vector of A and B crossed together is orthogonal to A which means that if I dot it with A, I should get 0. So this is a property. We also know that A cross B is orthogonal to B. So its dot product with B is 0. So that's just another way of describing this relationship here, is that the cross product between A and B is going to be orthogonal to both A and B. Okay, so we did something pretty similar for the dot product when we asked ourselves, what does this mean graphically, right? What does this cross product kind of represent? Okay, so let's try our best to kind of understand what's going on here. Let's start with looking at the magnitude of A cross B squared. Okay, so what is this quantity? What is the magnitude of A cross B squared? Well, if we scroll back up here, and I said that this was A cross B here in vector form, we're looking at the magnitude of this resulting vector, and we're going to square it. So we're going to get rid of that square root. So all I'm looking at is the magnitude of this vector here. We're squaring it. So we can write that down. This is A2 B3 minus A3 B2 squared plus A3 B1 minus A1 B3 squared plus A1 B2 minus A2 B1 squared. Okay. So what I'm going to do is I'm going to try to massage this right-hand side into something really nice. So I'm going to go ahead and FOIL these out and then kind of group them in a nice little way here. So this is equivalent to A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared minus A1 B1 plus A2 B2 plus A3 B3 squared. Okay. So let's look at these entries individually. Well, I have this A squared plus A1 squared plus A2 squared plus A3 squared here. This is the magnitude of A squared. So this is the magnitude of A squared. Now the second term here, this is the magnitude of B squared. So we have the magnitude of B squared. And if we look what's inside these parentheses here, this is the dot product. So we have minus A dotted with B squared. Okay, well, we know some properties about this dot product now. So let's continue kind of massaging this. This is equal to the magnitude of A squared times the magnitude of B squared. And I'm going to write down another property for this dot product here. Right, we're going to write it in terms of these magnitudes instead. So magnitude of A squared, magnitude of B squared times cosine squared of theta. So notice that both of these terms share these magnitudes in common, okay? So I can write this as the magnitude of A squared times the magnitude of B squared times the quantity 1 minus cosine squared of theta. Well, 1 minus cosine squared of theta is just sine squared, this term right here. So this is equal to magnitude of A squared, the magnitude of B squared, sine squared of theta, as long as we're having theta between 0 and pi. So notice that we started by squaring this whole thing, right? So I have that the magnitude of this cross product squared is equal to now this right-hand side where everything is squared. So at the end of the day, I can say that the magnitude of the cross product between A and B is the magnitude of A times the magnitude of B times sine of theta. And this is true when theta is between 0 and pi. So it's not directly the cross product itself. We're looking at the magnitude of the cross product, but it gives us kind of this relationship between what's kind of going on. We know that it has this direction that's given by that it has to be orthogonal to A and B. And now we have its magnitude here. So we kind of get the direction from this theorem. And now we know that the magnitude of A cross B is related to the magnitudes of A and B, as well as the angle between them. Okay, so the next part here might be a little bit difficult because we're doing some remote learning, but everyone kind of put their pencils down or whatever you're kind of describing or writing with. And we're going to talk about the right-hand rule. So the right-hand rule is a way to help visualize the direction that A cross B goes in. We know that it has to be orthogonal, right? But we have to determine which of the two vector or like directions that it can take. So what happens is I want you to take your hand and you're going to curl your fingers of your right hand to match the angle from A to B. So kind of maybe even place your hand on the desk. If A and B are both on the top of your desk and the angle is kind of going counterclockwise, that means you should be giving a thumbs up right now, right? You put the base of your hand down and A and B are on the plane of the desk. And we're kind of curling our fingers in the direction from A to B, right? So maybe I'll help draw it on the screen here. And then you can kind of put your hand on whatever. So imagine that we've got some vectors here. We've got A and we've got B, right? Just two random vectors that share some plane together. So we put the base of our hand in that plane. So maybe put it up against the screen. And we curl our fingers in the direction from A to B. So we're going counterclockwise here. And our thumb points in the direction that the cross product goes in. So in this case, the cross product is coming out of the screen. It's coming towards you. So whatever plane that they share, you put your hand on that plane and you just curl your fingers and your thumb should be pointed in the direction that the cross product is going to be going in. So in this case, pointed out of the screen. So you might look a little bit silly. Don't worry. I'm not looking at your pictures right now. So you can do it at home, whatever, turn your camera off. It's easier, I guess, than in lecture when everyone does it. We all kind of look funny, but we all have to kind of get some practice with this right hand rule. So now that we've kind of talked about the right hand rule, let's talk about some more properties that this cross product has. So two non-zero vectors that we'll call A and B are parallel if and only if A crossed with B is equal to the zero vector. So this statement here, you might not have seen it before, if and only if. In math terms, this just means that it goes both ways. So if I have that A and B are parallel, their cross product is the zero vector. If I have that their cross product is the zero vector, I know that A and B are parallel. That's what this if and only if means. It means that we can go, the first part of the sentence is equivalent to the second part of the sentence and vice versa. So this is a neat little way. We talked about how the dot product kind of represented how things are orthogonal. Well, now we can use this cross product to determine if things are parallel as well. Okay. Some more properties. So now let's imagine two vectors A and B again, forming a parallelogram. So let's kind of draw this out here. Put A right here. Let's put B over here. So we create this parallelogram. Let's grab all of them, move them over. So down here, I have this A vector, and here I have this B vector. If I draw a line straight down from B to A, and I have my angle measurement between the two here. So this is theta. Then the length of this red line here is the magnitude of B sine theta. Okay. The area of this parallelogram of this is A, which is the length, the base of this parallelogram, which we'll call the magnitude of our A vector, times the height, which is the magnitude of the B vector times sine of theta. Well, we just discussed above that this can be written as the magnitude of the cross product between the two. Oh, I missed a question about the zero vector. The zero vector is a vector of the same corresponding dimensionality where all of the elements are zero. It's not just the scalar zero. Okay, so in other words, the vector A and B form this parallelogram, and the area formed by this parallelogram can be described as the magnitude of the cross product between the two, which is pretty neat, right? Like if I give you some parallelogram that's defined by these two vectors, instead of giving you like coordinates or lengths of these vectors here, you could easily just take their cross product, look at the magnitude, and boom, you have the area of this guy here. Okay. So finally, let's talk about these last properties, kind of just a list. So the first property is that if I have A and I cross it with B, this is equal to negative B crossed with A. So this is a big distinction between the types of multiplication that you've seen with scalars and even the dot product, right? The ordering does matter here, right? And in fact, switching the order just makes a negative come out in front. Another property is if I have some scalar that we'll call D, and it's multiplied by some vector A, and now I cross this with the vector B, I can write this as D times A cross B, or I can write this as A crossed with D times the vector B. So scalars can kind of flow in and out of our cross product. Okay, property 3. If I have A and I cross it with the sum of B and C, I can write this as A crossed with B plus A crossed with C. So it does distribute. Property 4 is if I have the opposite, so I have the sum crossed with C, I get A crossed with C plus B crossed with C. So it distributes not only from the front, but it also distributes when it's the second term as well. Property 5, if I have A dotted with B cross C, this is the same as A crossed with B dotted with C. That's a huge property. And it's not very intuitive, right? There we have two different types of these vector multiplications, and it turns out that we can actually do these cross products of A and B before we do it with B and C. But mind that we have to do these in corresponding order, right? Because this ends up being a vector, and then we dot it to produce a scalar, and we still need a vector here. So we do the cross product first, and then end up with a scalar. So we have scalars on both sides here. So the cross product needs to be performed first. Property 6 is if I have A crossed with B, which is crossed with C. So we have to do this B and C cross product first. This becomes A dotted with C times the vector B minus A dotted with B times the vector C. So this is also another little unusual property, right? I have this double cross product here, so I have to do B and C first on A. This is the resulting formulation for that. It involves the dot product. We have A dotted with C times B minus A dotted with B multiplied by C. Okay. So we've got about 10 minutes left, a little bit of time. Give you a second just to write those down if you need to, and then I'm going to make a new page where we'll discuss the triple product. So we have two versions of this. We have the scalar triple product, is defined as dotting the result of a cross product. And one way to calculate this without the whole cross product and then dotting situation is we can write this as the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. So instead of doing the whole determinant just to calculate the cross product, if we have this dot product sitting on the left, we can write out this determinant like so. And this is actually pretty useful. Why would we ever want this scalar triple product? Well, imagine that we're now in 3D, and we're going to have kind of a similar situation here where we've got A, we've got B, and then we're going to have some vector that's not on the same plane as it. So this is going to make a parallelogram in R3. And then let me draw maybe in a different color here the edges of this shape. Let's do straight lines. So something like this, right? So we have our vectors here, and we'll write them as A, still two straight lines. Okay, so we have the vector A. We have our vector down here as B. And then we have a vector here called C. So I'm also going to draw one more line to kind of help us out here. The vertical line that comes out of the plane of B and C has some angle to this A vector. That we'll call theta. Well, the height of this parallelogram is the magnitude of A times the magnitude of cosine theta. Right, we want to keep height positive, so we'll put an absolute value around this cosine here. Right, so this is the height of our parallelogram in R3. So like rectangular prism-ish. So the volume is the area of this parallelogram in the plane of B and C times the height. So we get that the area from before was our cross product in magnitude. So we have the area here. And then we multiply this by the height, which is the magnitude of A times the magnitude of cosine theta. Well, this is the absolute value of A dotted with B cross C. So this is the scalar triple product, which results in some scalar value, and we're just taking the absolute value here to make sure that our volume is positive. So this triple product is actually pretty useful, right? Where in just the cross product could tell us the area of some parallelogram. This scalar triple product can tell us the volume of such a shape, which is pretty neat. Why don't we stop there for today, and then we can pick up with an example for next time, as well as just kind of finishing up section 10.4.